Hello and welcome to this session. We are super excited to tell the story how we set out to make it easier to build connectors for Apache Flink. So if you want to persist data in a destination that is not supported natively by Flink today, this session is for you. We have contributed an abstraction in Flink 1.15 called the Async Sink that makes it easier to build your own sinks. And today, we will not only discuss why and how we build that abstraction, we've also prepared a demo that shows you how you can use the abstraction to build a new sink yourself. So let's get started with how we ended up here. Apache Flink has a rich connector ecosystem, but there will always be use cases that require additional connectors. In particular, if you're looking at the destinations a Flink application may sync data to, there are just so many different possibilities that it's hard for the community to build and maintain connectors for each and every possible destination. And to make things worse, building high quality connectors is a lot of work. There are 5 key properties to obtain reasonable semantics and performance for a connector. And if you look at how sinks are built today, most of them are using batch requests to send a set of messages into the destination. And sinks do this to improve the efficiency and the throughput they can achieve. But in order to make batch requests, the sink first needs to start buffering messages and then monitor so-called buffering hints to know when to make a request. And once enough messages have been collected, the sink then makes a batch request, and it then needs to monitor the response for failures. So either the entire request can fail, but if you're syncing data in cloud-based systems that follow a provision throughput model, like individual messages of a single batch request may have been throttled. So you need to have like very fine-grained retime mechanisms built into the sink. And this protects you against failure of the endpoint or throttling of the endpoint, but it does not protect against failure of the Flink application. So if you don't want to lose, or if you don't want to risk lose messages, the sink also needs to participate in checkpointing to persist or protect the state of the sink and avoid data loss. And last but not least, the sink should be careful to not overload the endpoint. Right? So it needs to apply some kind of rate limiting so that it doesn't overload the destination and in the worst case, make it fall over. So we wanted to be able to support many more destinations with Apache Flink, but we're facing these challenges that it's hard to build and maintain connectors, in particular if they are developed independently. So we took a step back and realized, well, most connectors have very common requirements. They all do buffering and retries and checkpointing and rate limiting. So the idea was to build an abstraction that supports these common aspects of a sink. And when you want to implement a new destination or support for a new destination, you only need to specify those things that are specifically endpoint. So specifically how to make a batch request and how to inspect the response from that request to know which messages or which parts of the message were not persisted successfully. And the idea of the Async Sink is to have support for this common functionality. So to create a new connector, you basically only create a lightweight shim that specifies how to talk to the specific endpoint, and the rest is taken care of by the Async Sink itself. And this works well for certain classes of destinations. So in particular, if your destination supports batch requests, you can live with at least one semantics and you don't really care for ordering, or you can tolerate slight reorderings, then the Async Sink works really well to build a connector for this kind of endpoint. So here's how the Async Sink works internally. On the left-hand side, we have a message, and we want to persist this message reliably into the endpoint. And there's a lot going on So let's walk through this step by step. The first thing that happens is that when the sink receives a message from an upstream operator, it needs to extract those properties from the message that are essential to make the batch request later on. So if you think, for instance, of a streaming system, when you write a message into a stream, you need to specify the data or the payload, and often you also need to specify a partition key. And this is what the element converter extracts from the message. And once applied, it converts that into a so-called request entry. So the element converter basically takes a message, extracts all these required properties, and then creates a request entry that is buffered in an internal buffer. And this happens individually for each message that arrives at the sink. And at some point, we have buffered enough request entries that you can make a batch request into the endpoint. And this is done by the Async Sink writer. So the Async Sink writer basically receives a set of request entries and is then expected to make a batch request against the endpoint and inspect the response from the endpoint and watch out for failures. And all request entries that have been persisted successfully then need to be requeued into the internal buffer. And this protects against failure of the endpoint or throttling of the endpoint. So the Async Sink makes batch requests once there have been enough request entries collected, and then inspects the response that comes back to identify which request entries need to be requeued so that they can be retried later on. But it does not protect against failure of the Flink application. So for checkpointing, we need to add a serializer. So this is how checkpointing works. When a checkpoint barrier arrives at the sink operator, first of all, the Async Sink stops sending new requests, and it waits until all in-flight batch requests have been completed. Because then all request entries either have been successfully persisted in the endpoint or they have been requeued in the internal buffer. So if we want to preserve the state, all we need to do is basically serialize the internal buffer, and that's done by the state serializer. And then the state is included in a checkpoint, and Flink can leverage it for failure recovery. So if you want to implement your own sink, there are these three components that you need to implement. The first is the element converter that basically specifies how to extract those properties from the message that are required to make a batch request later on. The Async Sink writer specifies how to make a batch request and how to inspect the response. And last but not least, the state serializer specifies how to serialize the internal state, the internal buffer of the Async Sink. And that's all. So these are the three components you need to implement, and the rest is then done by the Async Sink. So all the buffering, retries, rate limiting, and checkpointing, this is done by the Async Sink for you. Before we look at how to implement a sink yourself, I'd want to take some time to look at how the Async Sink manages the fifth aspect, the last aspect, namely managing throughput and rate limiting the operator. So the challenge we are facing is we have an endpoint, and the Async Sink or the Flink application should not overload the endpoint. It should adapt to the throughput of the endpoint. So what we're trying to achieve is to adapt the throughput of individual subtasks to the throughput of the endpoint. But there are a couple of challenges. First of all, we don't necessarily always know what's the throughput of the endpoint, right? If you think, for instance, of a Kafka cluster, you may have a cluster with a certain number of topics, but you don't know the precise throughput for a specific topic. And even in case of cloud services that follow a provision throughput model, you may be able to discover the throughput of the endpoint, but that doesn't help if there are additional producers, because then you again end up overloading the endpoint unless you know how many other producers there are. trying to figure out what is the throughput and then adapt the subtask to that throughput doesn't really work well. And we are looking for something that is more self-adapting and doesn't require any knowledge about the throughput of the endpoint. And the responses we get when we make requests to the endpoint actually give us a quite good signal on whether the endpoint becomes overloaded or not. If a batch request, for instance, contains elements that were throttled, we know, well, at least some part of the endpoint are overloaded. And if the entire request fails or times out or gets slow, that's also a signal we can use. So we tried a couple of different strategies so that the subtask can leverage that information to adapt their throughput to the endpoint. And things worked okay-ish until we realized that this is actually a problem that has been solved before. So let me rephrase what we're trying to achieve. Instead of subtasks and endpoints, let's say we have a set of devices that want to send packets over a shared network. And we don't know the throughput of this network. And we cannot coordinate between these different devices. And if you think that sounds familiar, you're right. This is the same problem TCP has. So what we ended up doing is borrowing the congestion control strategy from TCP, which is called additive increase, multiplicative decrease. And applied to our problem, this is what we do. So first of all, we want to impose a limit on the number of in-flight request entries. And be aware, this is not the number of in-flight batch requests. This is the number of individual request entries, because that's the unit of work we want to control. And whenever we receive a response from a batch request, we take a look to see if that was successful. If it was successful, we just increase the limit by a constant factor, by adding a constant factor. And if throttling happened or the request failed, we simply cut the limit in half. And this is a very simple but very effective mechanism, and I'm still excited how well this works in our context. All we need to do is have two counters, one for the number of current in-flight request entries, and a second one to track the limit. And whenever we receive a response, we either add a constant factor to the limit or cut the limit in half, and that's it. So to give an example, like let's assume we are sending batch requests and we start with a batch of 10 messages. If the batch request is successful, we may send 20 requests the next time and then increase it to 30 and 40 and maybe 50. And if then a failure happens, we cut that in half back to 25. And then the cycle starts over again. So we're going from 25 to 35 and so on. So we are basically oscillating around the actual throughput limit for the specific endpoint. Again, this is like a very simple but very effective mechanism, and there are also fantastic theoretical results. First of all, there's no coordination required between these subtasks, which means it doesn't make any difference whether we have one application with 3 subtasks or we have 3 completely independent applications. So that's great. That solves the problem of not knowing how many producers there are. And if you look at the AMID strategy, there are results that show that if every producer uses AMID, each individual subtask converges to an equal throughput usage. So every subtask gets a fair share. So we are saturating the endpoint, but we're not overloading it. And every producer or every subtask gets roughly the same throughput, which is great. Now that we have covered how the Async Sink helps you to implement your sinks and cover these 5 aspects of sinks, let's take a look of what it actually takes to implement a sink by yourself.
We're going to walk through what it takes to actually build a sink based on the Async Sink framework. The code produced in this demo is based on a sample that can be found in the AWS Samples GitHub repository. And for additional resources, you could refer to the Amazon Kinesis Data Firehose and Kinesis Data Streams Sink that reside in the Apache Flink codebase on GitHub. So we're going to be using IntelliJ to walk through this coding sample. The scenario is going to be based around orders. So consider an e-commerce platform that groups products by categories, for example, outdoor, sport, music, and we want to generate metrics and store these in an external system that tell us how many orders have been placed for a given timestamp. So there are two projects in the Project Explorer. One of them is the Flink application project, and the other one is the connector project. These have been split in this way to show you the code that needs to be produced by the end user of the sink, so the Flink application that is using the sink, and what code is needed to be produced by the maintainers of the sink. So if we open up the Java code, go into the model folder, we can find order stats object class, which represents the aggregate orders that we were just talking about. So an order statistic has a count, timestamp, and category. So the number of orders for a given timestamp and for a given category. So we're not really too fussed for this demo where this data comes from, but we can assume there's some upstream system that generates us these metrics. For the purposes of this demo, we're going to be using Lombok. So it will generate our getters, builders, etc., and reduce the boilerplate for this demo. In the source package, we can see there are two data generators. We have a sawtooth and a sine wave data generator. These will generate a batch 2 hours worth of data and then one record every second to simulate data for the demo. So let's get coding. So this is the main method for our Flink app, and we're going to start off by creating some source functions. So we're going to create an outdoor data generator generating sine wave for outdoor category. And also we're going to use the sawtooth one to create data for the music category. We will add these to our job graph and return the stream. So outdoor stream and the music one, add source. To show you the data, we're going to union these two streams together. So union outdoor with music, and we'll simply print this for now, and we can see the shape of the data. So let's run this. There we go. So as I mentioned, we've generated a batch of 2 hours worth of data, and then every 1 second we get a new record. We can see the count, timestamp, and category, be that outdoors or music, and over time the count should form a sine wave or a sawtooth wave depending on the generator used. Okay, so this is our Flink application that's processing the data. Now let's create a sink that allows us to persist this data somewhere. For the purposes of this demo, we're going to be creating a CloudWatch metrics sink. So CloudWatch metrics is an AWS service which allows us to persist and visualize metrics. Within the console, we can visualize metrics using the graphs and various widgets. So it's quite powerful, especially for a demo. So I'm going to reopen the Explorer over here, and then I'm going to jump over to the connector project. So there are 4 main classes in here, 3 of them which constitute the building blocks that we've previously discussed. So we're going to start with the element converter. An element converter implements element converter, and the job of this is to convert our record into a type that could be persisted to our end destination. So for CloudWatch metrics and the AWS SDK in particular, we are interested in this metric datum object type. So the metric datum has a metric name, a value, a timestamp, and dimensions. So there are various other fields, but for this, we are just going to be supporting these set of fields. So we need to convert the record into a metric datum. So for this demo, the metric name, we're going to have that static. So you'll create a sink. You can only create metrics with one name, but you could change this if you like. So we'll simply pass the metric name through And then the final three fields we'll actually extract from the record. To do this, we're going to use a functional interface called function, which accepts type T, and for the value, it will extract a double, and we'll call it value extractor. This way, we can simply call the apply method on the record, which will extract that value from the record. So we'll follow the same pattern for the timestamp and for the list of dimensions. And we'll call them dimension extractor and timestamp extractor. And follow the same pattern down here. So this is our element converter complete. And just to reiterate, this will take a record and it will generate a metric datum. The next class we're going to look at is the sync writer. So this class is responsible for writing the metrics to the end destination. So I've already coded some of the boilerplate here. The first thing is we're passing in a namespace. So within CloudWatch, a namespace is a logical container for your metrics. And we can see this being used with AWS services to separate metrics between, for example, Lambda, EC2, etc. As a user of CloudWatch, we can create our own arbitrary namespaces. We also have a HTTP client and a CloudWatch client, which is used to write to CloudWatch. There's some configuration options here, which configure the underlying behavior of the Async Sink, and we'll go through these in a bit more detail later on. And then finally, we're instantiating the clients and setting everything up ready to write to CloudWatch. So the actual bits we're going to implement are down below here. So we have submit request entries. This method is responsible for writing the metrics to CloudWatch and handling any failures. So let's get started with this. We need to create a put metrics data request, which again has a builder. This request accepts two parameters, namespace, which we've previously discussed and passed in, and a series of metrics to send. So the Async Sink framework has passed us a batch of metrics to send, and this is the batch we're going to persist in CloudWatch. So we've created our request. Now we need to actually pass it to the client. So async client, put metric data, request. And this is going to return us a future. Because this is an asynchronous client, it returns a future, and then we're asynchronously going to handle the result of this. So future when complete, we will receive a response and an error. So this is where we need to look at the response and the error and decide, did this data get persisted successfully? Were there any problems? Do we need to retry any of the elements? So for CloudWatch, it's an all or nothing. Either all of the metrics are going to be successful or none of them are going to be successful. So this simplifies this method for us. So we're simply going to say if error is null, that means there was no problem and all of the metrics were persisted successfully. So we will use this failed metrics callback, which is where we pass back to the framework which records we need to retry, and we're going to pass in an empty list because there's nothing to retry. So this is the happy path complete. So else there was a problem. We're going to re-enqueue all of the metrics to send, and then the Async Sink framework will retry that request. And it's worth noting at this point, you could implement any custom error handling. So you may want to interpret the exceptions and apply different behaviors depending on the error code. In this case, we're going to retry. If you did want to fail the job, there is a method you can call get fatal exception consumer, and then you can pass the exception in and it will fail the job for you. And then Flink will behave depending on your failover strategy. But for the purpose of this demo, we're simply going to finish with this, but we will add some logs so we can see what's happening. So I'm going to say sending batch of metrics, pass in the size. And then when we're successful, send batch. And if we fail, we're going to say fail to send batch. I'm also going to print out the error. Okay, so that is the sending part of our sync complete. The next thing we need to implement here is get size in bytes. We'll talk about it later, but there are various configuration options you can set up for the async sync. One of them is to set up the maximum batch size. And in order to work out the maximum batch size, we need to know the size of each record. So this particular method is a lot easier to implement for something like Kinesis or Kafka, where we're given a byte array. In this case, we need to extract the number of bytes that are going to be persisted. So we have set the metric name, which is a string, so we can get the length of that, and times 2 to get the bytes. Then we also have a timestamp, which is a long, so we'll give it 8 bytes for that. We also have a value, which is also a long, so we'll give it 8 bytes. And then we also have a list of dimensions. We're going to use a stream and sum up the length of the value and the name. So map to long, going to take the dimension name length and the dimension value and multiply them both by 2 and then sum. So this will give us the number of bytes that we have generated in our metric datum, but depending on the underlying implementation, this may vary. For example, we may be compressing these records. We may not be using the full 2 bytes for each character. We may be using ASCII or some other encoding. So we would have to double check to make sure this actually lines up with our client and the way it sends it. And then finally, there is a close method here at the bottom, which is used to close the clients at the end of or when the job is finished or cancelled. So just to summarize, this was the implementation of the CloudWatch metric sync writer, which is implementing or extending the async sync writer. It accepts our generic type T, which is our record type, and it persists metric datums to the end destination. So taking a look at our project structure again, the third piece to the puzzle is the state serializer. So we're not going to implement this, but I'll briefly show you it. It simply needs to serialize our metric datum to a data output stream and another method to deserialize a data input stream to a metric datum. And this is used to allow the sync to participate in checkpointing and to serialize a state and then deserialize the state. And then finally, we have a class here to wrap everything up together. So this one is already implemented. I just need to uncomment some code to make it build. So we're constructing the element converter. We're passing down some default or some dummy configurations for the base sync, which I'll discuss in a bit later on. And then we have some creator methods to actually instantiate our sync writer and our state serializer, and then some helper interfaces here. But this class is mostly boilerplate. So now we've completed the sync, we are ready to wire it into our sample app. So we're going to go back to this app, which we've just created, and we will build a CloudWatch metrics sync. So again, we have a builder. So we'll pass in a namespace. So I'm going to use the namespace AWS demo. We need a metric name. So we'll have count because the metric is the number of the count of orders for a given category. The value extractor is the callback used by the element converter. So the value extractor will take an order stats and it will return the value of our metric, which is the count, which comes out of the order stats. The timestamp looks very similar. And the dimension extractor. So we can return an arbitrary number of dimensions here, but for the sake of this demo, we're going to add a simple one, which is a single dimension, which is the category. So we'll create a new dimension, which has a name of category and a value of order stats.getCategory. And then finally, we will build this. So because we're using an AWS client here, we also need to pass in some client properties. So within the AWS base connector package, there are some standard keys you can use to configure the underlying clients. And this is a property map which will be used to pass these through. We're simply going to configure the region. So the class is the AWS config constants, which has a region. And for this demo, we're going to be using US East 1, and then we'll pass that into the sink. This is something else that I pre-configured. So now the sync's ready to go. Instead of printing, we are going to sync to the CloudWatch metric sync. And I'm going to restart the app. So the application is now running. We can see we're sending batches of 1,000 metrics, sent batch of 1,000 metrics. If we jump over to CloudWatch in the AWS console, we can see custom namespaces, and we have the AWS demo namespace, which is what we've just created. Under that, we have a metric with one dimension, which is the category which we've just created. And then underneath that, we have our two categories, music and outdoor, and our metric name of count. So let's add these both to the graph. We can see here our sawtooth and our sine wave patterns. We've generated 2 hours worth of data, and now every 1 second, we're going to be pushing new metrics out. So we can see the number of metrics started off at thousands because that was our maximum batch size. Now we've caught up, we're down to 20 metrics roughly at a time. So the sync is working as expected. So now I'm going to demonstrate the AIMD rate limiting strategy in action. In order to simulate some failures, I'm going to increase the maximum batch size above the limit allowed by CloudWatch. So CloudWatch allows a maximum batch size of 1,000, and we're going to increase that to 1,800. This means we'll try and send a batch that's too big, it will fail, and we'll start seeing the rate limiting kick in. Jump back to the sample project. We can see all of this in action just by viewing the logs. So if I run the application, then we'll start to see some logs coming out. So we can see here the sync is sending a batch of 1,800. It failed due to the metric data having a size greater than 1,000. So since this failed, the AIMD rate limiter will kick in, and the next batch we will send is going to be 900. This will slowly ramp up, so 9, 10, 20, 30, 40, until again we see a failure. So we go above 1,000, fails to send 1,010, which fails, and then we half that back down to 505. And then again, the same thing happens, it will start ramping up. So this demonstrates the AIMD rate limiter in action. Okay, so now the demo is complete, we're going to look through the internals of the Async Sink and how the configuration can be used to tweak different aspects of the actual underlying framework. So we have this internal buffer, and we also have batches. Within a batch, we have records, and this configuration option, max record size in bytes, is used to configure the maximum size or the maximum number of bytes per record. If you try to enqueue a record with a number of bytes greater than this value, it will be rejected and fail the job. Then we have two configurations which are used to configure the size of the batches, maximum batch size and maximum batch size in bytes. So these are going to be much like the last configuration option. These will be dependent on the end destination and what batches it can handle. We have max in-flight requests, which is essentially how many requests in parallel can be made to the destination. We have max buffered request entries. So this is used to configure the size of the internal buffer, and it's also used to control back pressure. So if the maximum number of buffered request entries is exceeded, then the sync will stop accepting new records and it will apply back pressure to the job graph. And then finally, max time in buffer milliseconds. There are 3 eviction strategies or flush strategies. One of them is based off the number of bytes, one of them is based off the number of records, and the final one is the max time in the buffer. So if a record sits in a buffer for too long, we can then flush that, which is useful for low throughput situations. We've discussed the Async Sink framework and the benefits of it, but as always, there are some limitations, so let's go through these. The first one is the at least one semantics. We don't support out of the box exactly once semantics. The sync doesn't implement the two-phase commit interfaces. However, you could implement them yourself on top of the async sync by implementing the appropriate interfaces. Due to the multi-threaded nature of the sync, ordering is not guaranteed because we allow multiple requests to be performed in parallel, and we also allow partial failures. So for example, if within a batch of 10 records, the middle 2 failed, we would then re-enqueue them and they would arrive out of order even within that batch. You could simulate ordering if you reduced the maximum in-flight request to 1 and you didn't support partial failures, but at that point you're really not leveraging the benefits of the async sync, and it might not be the best framework for your sync. And finally, thread pool management. You may have noticed in the demo that we were using the AWS SDK asyncs clients, which have their own underlying thread pool, and we were also closing that down. So the async sync does not manage any thread pools for you. As a sync developer, you're in control of that. And if your destination does not supply an async client with thread pools, you would have to manage them yourself. So what's next? For Flink 116, we have Flip 242, which is configurable rate limiting. This allows the sync developer to control what, how much, and when the rate limiting is applied. So before this, we would default to the AIMD and it was not configurable. So as of Flink 116, when you build a sync, you will be able to specify whichever rate limiting strategy you wish that fits your needs. We are working on Flip 252, Amazon DynamoDB sync. So we're working on this in a review and test capacity. This is actually being contributed by the community and we're helping out with the review and testing. Finally, wider community adoption. There are a range of other syncs that have already started using the Async Sink framework. We've seen Flips, so for example, Redis. We've seen Jira's for Cassandra and other destinations. So it's exciting to see the framework being leveraged, and also just discussing with people at Flink Forward, it's already being used internally. So that's great to see. So we set out to make it easier to build syncs, and we've arrived here with the Async Sink. We've really enjoyed working with the open source community, and it's great to see people using the framework and great to hear everyone's feedback. Thank you.